If I have some planet, I'm going to label planet X, and I launch a satellite from it. I don't think it's officially a satellite because I'm not going to have it orbit. I'm just shooting it straight out. Assume that there's some propulsion to get it going, but once it gets going, there's no more propulsion and the thing is just traveling on its own. So the only force acting on it is the force due to gravity, acting backwards. The planet also has a force due to gravity acting up in the opposite direction because of Newton's third law, but this is the one we care about. This is a conservative force. So, therefore, let's take a look at that work-energy relationship. This is equal to the conservative force dot dx, as I've used other places. Dr works just as well since we're dealing with sort of a radial direction. That seems most appropriate. And that's equal to negative u final minus u initial. My conservative force is the generalized force due to gravity. So this is negative g mass 1 mass 2 over r squared. Mass 1 mass 2, mass x and mass s for satellite. So that's, just put a little s right there. Rx hat dot dr is equal to negative u final minus plus u initial. Rx and dr. Rx is a radial unit vector centered at planet X, and so it is in that direction. Dr is the differential that is positive in the same direction. So those are in the same direction. So I'm left with negative g mass of planet X, mass of the satellite, times the integral of 1 over r squared dr from some initial to some final distance is equal to u initial minus u final. Integrating this, I'm integrating r to the negative 2 dr. You add 1 to the exponent and then divide by that. So this becomes negative g mass of x, mass of the satellite, times negative 1 over r from r initial to r final. The negatives will cancel out. And I'm left with g mass of planet X, mass of the satellite, over r final, minus g mass of x, mass of the satellite, over r initial, is equal to u initial minus u final. Now all I've done is derive in essence, the conservative work here, and I know it's equal to the negative change in potential energy because of the way we've defined things. The question is, what does u equal so that this works? And if you've seen presumably I have it in another video, but there's actually an infinite number of solutions. There's a basic part to it that is generally written as the formula. However, recognize that's not quite true. So I would suggest pausing this, trying to figure out what formula could we use for u so that this is true. And then welcome back from pausing. If we let u equal negative g mass of x, mass of the satellite, over r, well, let's see if that works. So ui, so this becomes negative g mass x, mass satellite, over r initial, minus negative g mass x, mass satellite, over r final. That becomes positive, and that's negative. That works. If that's my formula for potential energy, this works. But there are others. So I have u is equal to negative g mx ms over r. And I want u initial minus u final to equal g mx ms over rf minus g mx ms over ri. Can you think of another formula for u so that this works? And I would suggest pausing it, trying to think of another formula for u so that this is true, so that this works. So pause it. Welcome back. If we let u equal negative g mass of x, mass of satellite, over r, plus some constant, and I'm just going to use the letter c for the constant, doesn't matter what it is. Well, let's make sure that that works. So my u initial minus u final would be negative g mx ms over r initial plus some constant minus negative g mass of x, mass of the satellite, over r final, plus some constant. When we distribute the minus sign here, that becomes positive, and that becomes negative. My c's cancel out, and I'm left with what I had before. So there are an infinite number of solutions here. People often sort of forget about the fact that I can add a constant to it. Now, typically, you need to state where is this equal to 0. You need to establish what the constant is. The most usual constant that we pick for this is that if r equals infinity, u equals 0. And so that means we get an infinite quantity on the denominator, making this infinitesimally small, plus some constant has to equal 0. And so this would imply that c is equal to 0, but it doesn't have to be. And that's the derivation of the formula for generalized gravitational potential energy.